Stephen received his bachelor's degree in physics and computer science from the University of Queensland. Stephen received his PhD in computer science in 2008 with an emphasis on emotional expression in music. He worked as a research associate at Bill Thompson's at Macquarie University in Sydney, and from there went on to work in Kevin Palmer's production lab at McGill, where he worked on motion capture and speech and song. Starting in 2011, this last year in October, Stephen joined us here at our
Great. Well, thank you, Frank. Thanks everyone for sticking around. I know we're over time, so I'll try and keep this nice and brief. So thank you to Naresh and Frank for inviting me to speak today. The work I'll be talking about was work that I did during my dissertation. Okay, so the direct question that I had for all of this work was whether we could take something as abstract and ephemeral as emotion, particularly emotional music, and whether we could take that, whether it could be understood, whether we could take emotions and music and somehow quantify them. And if we could then take this quantification of emotion and music, if we could then leverage that in a computational system to change music and emotions. As you probably know, one of the most salient aspects of music is its capacity to arouse an emotional experience in listeners. Surveys have shown that music is ubiquitous in everyday life, and that listeners often use this to create an atmosphere to evoke the right emotional experience. Industry has long used the expressive power of music in a variety of applications, as some of you see today. It's been frequently used in modern use in cinema, television, and video games. It's this last application, video games, that actually I was particularly interested in applying this to work. Video gaming, as you probably know, is a major industry these days, but it also poses unique challenges to composers, given the inherently non-linear structure of video games. Whereas in cinema and television, composers can simply pre-compose a score for a fixed timeline and narrative. You can't really do this in video games where the game flows on in real time. It's essentially dynamic. So composers have met this challenge by employing dynamic audio, typically where event triggers load pre-composed tracks and sound effects. However, this is generally a rather coarse method. It doesn't really address the underlying real-time nature of video games. So I thought an alternative approach might be to develop a system where the emotion of the music can be adapted in real time to match the game state. So that was the application that I used to secure additional funding for this project. At this point, I was kind of at a fork in the road. I could have taken the machine learning approach, which we've heard wonderful developments across today. But instead, I decided to take a more perceptual approach, because I think, as taking the quote that Duran Wiggins made, the original one, music is a perceptual phenomenon, and we should recognize that when dealing with music and computing. So, thankfully, for over a century now, psychologists have been examining the relationship between musical features and their emotional consequence. Just one of the most well-known is the association of major mode with psychiatric music, minor mode with sad music. Just to underscore this, just recently in 2009, they found that this association might actually be culturally universal. Even for people who haven't been exposed to Western music, they showed a slight bias with major and minor modes. So there's definitely something to work with there. So my approach then was to collate these perceptual relationships into a set of rules that essentially govern musical emotion. So in my thesis, I collated 148 empirical studies on emotion. These were sourced from 4 independent meta-studies. I then rank ordered these relationships between musical features and emotion based on the number of studies that cited it, and relationships with 3 or more congruent citations valid. This is just one half of the rule set. I won't go into too much detail here, other than to say that I collated citations and categorized them into 4 basic emotion categories. Across all the rules, there were 387 music relationship emotion relationships, and the rate of agreement across all of these, across 148 studies, was around 88%. So most of the researchers did a pretty good job in having these aligned. So I'll just give you one example. 19 independent studies said that fast tempo is typically associated with a happy work, whereas one study said it's typically associated with a slow work. So So most of the time the studies tend to agree. So then taking this, all of this information, I developed a rule system. I codified 8 what I'm calling music emotion rules. Also, I won't go into detail today, but 7 humanistic performance rules. This system was working on symbolic MIDI input, meaning that it lacks all expressive information. So another task I had to overcome was making somebody humans playing this music, because we're dealing with emotion. We can't have emotion without having a human. So that was another part that I'm not talking about. Yet symbolic MIDI input, and it's got some real-time architecture for applications. So here's just a pretty picture of how it works. We have the MIDI file that goes in with a bit of markup information that describes the phrase structure of the work. Pre-process it for a couple of milliseconds, and then it starts playing it in real time. Essentially, you're the operator down here, and you say, hey, I wanted to have this particular emotional description. Naresh already talked about the arousal valence structure. That's how the system works. You basically just plug in a coordinate value, hey, make it happy, and then just enables a bunch of filters in real time, and it changes the emotion of music. So, I'm just going to play for you now a couple of examples, because let's face it, when we're dealing with computers and music, I always want to hear the audio first. So, I'm going to play you some samples now. So this is a fragment of Mozart Piano Sonata, and this is just the emotionally unmodified, in its normal state. But it has been made to sound like a human's playing. So now I'll play you a version which was made to be sad. The last one I was playing for you was angry, because we're running short on time. Again, because we're dealing with essentially perceptual stuff here, I had to run a couple of experiments. I'm only going to talk about one of them today. The experiment had 20 listeners. There were 3 musical works, a Beethoven piece, a Mozart that you just heard, and a piece by Mendelssohn. I generated 5 versions for each of these musical works, a piece in its normal state, and then these 4 basic emotions that I hoped to make it sound like. In this task, people just had to continuously rate the arousal valence of the piece they were listening to. Okay, so there were a couple of dependent variables. What I did was I reduced the data set down to mean arousal valence values for each audio that they listened to, and then I codified accuracy, that is whether that mean value fell within the particular arousal valence quadrant that the system intended it to be within. There were a bunch of statistical analyses, and I'll just get onto the data. Okay, so this figure basically shows how accurate the system was. Down here are each of the 4 emotion categories, and for each of the types of musical works. The binary logistic regression found that the system was usually significant in its attempts to change the emotion of these works in these various quadrants. And the overall accuracy was around 78%. So it did a pretty damn good job of what I wanted it to do. Okay, so this is now showing a little bit more detail of the arousal and valence shifts. So this is the valence figure. You can see this is where the work started off, just the normal Mozart or normal Beethoven. You can see there's a nice distribution, and I actually chose the works for that reason. But then when I told it to make the work happy, it all sort of converged into nice positive valence. Then for angry, it went to negative valence, and then stayed at sadness, and again, the tender. Similarly, for the arousal, there was a distribution initially to show that the works weren't all homogeneous, and then it successfully shifted them to each of the respective locations on the figure. So, what can we take away from all of this? That the emotions of musical works can change simply by modifying the underlying musical features. and that I was able to derive rules from cognitive studies, and they were in fact highly effective at reading about this, these changes in emotion. And as such, I feel that this has particular applications in music information retrieval. It doesn't all have to be governed by machine learning. You can make use of the enormous data set that's out there that's been done by psychologists, and you can probably get some very good results out of that. And finally, the system was actually developed originally for real-time applications like computer games and immersive environments. And that's where I got to. Okay, I'd just like to thank my collaborators in this project, my two supervisors, Ralph and Andrew, and Bill Thompson for providing guidance towards the end. Thank you. Questions? Yes, Mike.
Nice work, thank you.
Thank you.
And so you were working with kind of monotemporal sources. I have two quick questions. One is, did you consider a wider range of repertory to try and modify?
Yeah.
And are we seeing kind of S3 examples?
Yeah.
That's one question.
Fair question.
And the second is, did you try, what would you do with multi-temporal?
Right, yeah, actually that's a really good point. So in a sense it's only monophonic, it's only working right now for piano, so piano music or cello or violin, whatever the types of, it's only simple voice music right now. For me this was more of a proof of concept that we can do this, rather than trying to meet all of the challenges posed by the music. As to whether these samples would cherry pick these, no. I think the testing results kind of demonstrate that I didn't cherry pick them. I don't think there were really any statistical differences between the three works. Interestingly, while this wasn't really a goal of the project to create a realistic human-sounding machine performance, when I asked people post after the testing, nobody realized that these samples were generated by a computer. They all thought they were human performances that I listened to. I honestly thought that I could hear them when I coded them. No, they weren't the best samples. There is a bit of variability in terms of which ones sound the most real, but in terms of the emotional effects, they were all very similar in terms of what they did.
So a technical question about going from a major mode to the minor mode, because obviously when you go from a major to minor, there are sometimes some intervallic problems
Yes.
when you do that.
Yeah.
Did you have to do sort of manual operation to tweak them, or have you got some algorithm which does that for you?
No, yeah, you're right. In one of the samples, there is an intervallic error when it does do that. I was willing to accept that for the one or two errors that it had, because...
So did you tweak them?
No, I did not tweak them.
Oh,
no,
right.
no. Whether it sounds... I guess you just have to listen to it and see whether you feel it affects the emotional piece of the work. Yes, no.
Given that you have information on where all these changes took place, what do you think, or do you think this would be a data set and a process that would be useful for looking at what is the sort of sustaining emotional cues of a work, in terms of some cues being incidental and rare and some cues sort of being lasting? So for example, if you're playing in a particular mode, you can have a sustained harmony that will then continually, constantly remind you of that.
Yeah.
Whereas in other instances, you can have very fleeting cues that will, like articulation changes that can then confuse those things. So would this be an interesting avenue? Do you have that kind of information to then look at that time course?
Yeah, actually that particular question was one that I was concerned with when I was working on real-time aspects, because particular features like the mode, for example, you can't just suddenly switch between modes in real time in the game because it's very jarring. You have to choose appropriate structural locations in the music to make these shifts, whereas things like changes in dynamics or perhaps articulation can be more immediate in real time. So there's a whole complex logic there when to enable each of the filters. I didn't talk about that today, but the answer is yes. I'm well interested in that, and I think it's worth investigating in the future. Yeah.
Any rule that, I know a lot of rules must seem somewhat logical. Any rule that take you by surprise? It's just curious.
Actually, the rules that took me by surprise were the ones that came out of machine learning. I think that's generally the way it tends to be. Most of the psych ones, just taking a quick look, No, not really. No, they're pretty much all like from as a pianist. They're all seem pretty logical to me. Yeah. That's correct.
How does your system compare to other expressive performance systems? So let's say recursive presence.
Yeah, directed music. You mean in terms of humanist performance or the emotional?
No, the emotional.
Okay. I didn't ask that question because I have extra slides. Okay.
It's not planned.
I know it seems like that, but no, it wasn't.
To talk about this work, in fact.
No, actually, I just added at the end, like that's just the last one. I thought, oh, I should probably add these slides just in case of nuts. Yeah. So some of you may have heard of this directed music system. It was done back in 2000 by Roberto Brezin and Anders Freeberg. Lovely chaps. I spent some time with them a couple of years ago. So yeah, I got this question quite a few times. How does your system compare to the existing one? So I actually tested it. Basically the same sorts of tasks. There were two music works, two for my system, two for theirs. And I basically ran the same sorts of results. This is a breakdown of how the two systems did in terms of accuracy. There's mine in the dark, and theirs directed music's in the light grey. I don't actually have the actual accuracy. I know mine did a lot better. And then actually in terms of how it was a lot better, this breaks down the arousal and valence aspects of it. So in terms of arousal, these two weren't significantly different, I don't think. But there was a huge difference in terms of how the two systems modified valence. This is an easy one to change, arousal in music, just speed it up, make it louder. Valence is a lot more complex and actually relies on changing structural aspects in the music, which is what this system of direct music didn't actually do. It just modified performance, things like articulation, whereas mine actually changed the structure like mode and pitch height and those sorts of things. And that's actually what sort of critical valence, which kind of taps into our earlier talks today. Yeah. So, yes, I have compared. Yes.
So one last question. Obviously, the studies and the system depend on a certain consistency in the corpus on which they're analyzed. Can you say something about range of music to which these require?
What types of range of music?
Yeah, so we heard classical piano music in the early 19th century.
Oh, right, yes.
What other kinds of music might this be?
Yeah, sure. I was actually really interested in applying this system to modern pop music. I think some of these rules would apply, others would not. I think the majority of basic musical rule bases, given it's based on Western tonal music, would actually apply. And that's basically where it's stopped. Prior to these two experiments, I did actually take some Japanese music from The Legend of Zelda and another piece from Mozart, and I ran the system through that, and it was equivalent. It was almost equivalent in terms of it was able to change the Zelda Japanese music almost as effectively as the Mozart piano sonata. So I think it's an open question.
They were the same listeners, though?
Yes, same listeners. Yeah, so you know, they got the Mozart, they blocked around mice, and they also got the Zelda piece of music, and they're almost equivalent in terms of the emotional shifts that the system can do to the music.
It's quite interesting that most people who analyze and discuss the modern classically oriented video game music will cite the early 19th century repertoire as being the source of its courses and its great impact.
Yeah, yeah.
So kinds of pop music too.
Yeah, I was actually interested in applying this then to popular music. Yeah, most of the stuff.
Can I just ask, if I remember correctly when you played Mozart, you went to the parallel minor?
Yes. Yeah.
So is that basically the structural shift which you're doing when you go into the parallel?
Yeah.
Did you look at going to the minor? Just thinking about, you mentioned the shifts to Fujari.
Yeah, it was, when I say often, like, in one particular piece, there was one interval where it was. It sounded correct, yeah.
Right. Okay, but if you're modulating from minor mode to major mode,
Yeah.
or vice versa, you're going to go. If you're going to go from the parallel majors to the parallel minor, that is possibly it's less frequent in the repertoire than going from the relative major to the relative minor, or vice
yeah.
versa.
I think
Because of the key signature relationship.
Yeah, I'd have to go back and look into my notes of why the change occurred. But I think the reason I chose the parallel was because I couldn't include a overall pitch shift. I know there was a reason for that, and I think it actually led to one of the questions in pitch height.
Okay, because I would have thought going to relative minor would actually be beneficial because you're going down in pitch height.
Yeah.
Which is going to be one of the rules.
Oh, well, that's the problem. Well, that's actually a separate rule. So while sometimes, so mode is associated with the valence, but change in pitch height, I think, was actually more commonly associated with arousal. So it actually, it varies sometimes.
Sometimes you want it, sometimes you don't.
Yeah, exactly.
Okay.
Yeah, yeah. So pitch height high is often associated with happy and angry. So these are two where the valence are different. So that's why I actually had to separate that out and use the parallel, because I didn't want to confound two